Over the years, I've accumulated experience in the dynamic field of data science and data analytics. In my professional journey, very recently, I've started serving as a freelance data science trainer. In this capacity, I design and deliver comprehensive data science courses tailored for fresh graduate as well as junior level data scientists. My passion for data science stems from the fact that data has a transformative potential for businesses and industries. Through my training initiatives, I aim to impart practical skills and knowledge to the next generation of data specialists, bridging the gap between academic theory and real world application. I find great satisfaction in witnessing those great moments during the training sessions when complex concepts click for students. Currently, I'm excited to be here sharing my experience and learning from this vibrant community. Let's embark on this journey together where the data science is not just a field of study but a catalyst for innovation and meaningful impact. Thank you for having me. Today, we are diving into a fascinating piece of code that combines image processing and convolution neural networks for image classification. The code is split into two files, process py and app py. Let's explore the key functionalities and the high level flow of this exciting project. Firstly, in the process py, we have two crucial functions. The very first one will be actually block image. Let's just write this down and see how it really looks like. Firstly, we need to actually import a couple of modules from TensorFlow. Keras will import layers and models. Then we need to define the block image function. Inside, we'll give image as an input. We need to define height and width, which is simply to get the pixels. So let's just write, then I'll explain every single part. So the feature will be our simple list, empty list. Then we have to run loops for range in shape 0 minus height plus 1 height. Then we have to have origin range 0 shape 1 minus width plus 1. Then in the end, we need to get the image blocks. Simply, we will need to have actually the block pixels basically. So this is going to be our block image. Then we have to append the block flat version of it. This is just simply to get the 1D array. Then we have to return feature. So this function is actually takes an image and as input divides it into small 8 by 8 pixel blocks and then flattens each block into a 1T array. The result is a list of these flattened blocks which will be used for feature extraction. So the second part will be actually simple CNN. Inside we'll have train data as well as test data. Train data is simply for training the model on it, and then we'll have to evaluate the final model on test data. So let's just have the model inside models dot sequential. Inside we have to use convolution layers. We have to put a couple of parameters inside. So we'll have the filter sizes, activation function, which will be relu. Relu is actually release good activation function simply because it can avoid dead neuron problem. Let's have the second layer. This is going to be max pooling 1D. We'll have just two of them. Then convolution 1D again. This time we'll use actually 64 and filter size. Then we have to have the activation relu function. As I mentioned earlier, relu and leaky relu are good activation functions to avoid dead neuron problems. Then we have to flatten the layers. In the end, we will just simply put two dense layers, mix into layers, activation functions as usual. And the output layer, which is to get the final result saying that if it is a banana image or berry image, since we are doing just image classification. We have to compile the model. The optimizer will be ADAM. This is the default, actually. Then we have a couple of loss functions. That's going to be categorical cross entropy. Then what kind of metrics we will be using? Obviously, the metrics is supposed to be accuracy. Simply, we are trying to see how accuracy result changes per each epochs that I'm talking about. So X train, Y train will be our input. Then we have batch sizes, which is going to be 32. Then we got epochs. So it will run on 10 epochs. Validation split. Split will be 0.1. Then we got the final return model. All right, so the second function, CNN simple CNN, is where the magic of convolution neural networks happens. Using the Keras library, this function defines a simple CNN model. It compiles the model with the ADAM optimizer and categorical cross entropy loss, and then trains the model on input data for a specified number of epochs and batch size. The train model is then returned. So here, there's also one more thing we have to define. The CNN simple function is employed to build and train CNN model using the preprocessed data. The model makes predictions on test data, converting the results to human-readable labels, BlackBerry or banana. The predict label is then returned. So here is several, actually here a sequential model is created using this Keras API. It is actually consists of several layers. The very first layer is convolution, 1D convolution layer with 32 filters, a filter size of 3. Then we have ReLU activation function and input shape of 192.1. The numbers 64 or 32 and 3 represents the hyperparameters of that particular convolution layer in neural network. Let me break down these values. So the number of filters define how many different features or patterns the layer can learn. In this case, the layer has 32 filters. Increasing the number of filters allows the network to capture more complex features in the input data. However, it also increases the computational cost. The choice of 32 filters is somewhat arbitrary, and it's often determined through experimentation and tuning. And the filter size of 3 represents size of convolution kernel or filter. In this case, the filter size is 3. A filter size of 3 means that convolution operation considers 3 consecutive values at a time. Smaller filter sizes are effective at capturing local features, while larger features filter size can capture more global patterns. The choice of 3 is common and can be effective for many tasks. The specific values, such as 32 and filter size of 3, are often chosen based on the nature of the task, the complexity of data, and empirical testing. There is no one size filter or size fits all answer. It's common to experiment with different hyperparameter values to find the configuration that works best for a specific problem. If you were to choose different values like 65 and filter size of 4, it might still work, but it would be different configuration that could have a different effects on the model's performance. The optimal hyperparameters can depend on factors such as the size of input data, complexity of patterns you are trying to capture, the available computational resources, etc. So we have just finished this model part. Let's just move on to app.py. We'll actually import a couple of libraries, modules. Let's import IO. Then from scikit-learn model selection, we will simply import train test split just to split the data into train and test data. Then we have to use actually a couple of extra, like import pandas as PD. This is just to simply create the pandas data frame, import numpy as MP. We'll use actually a numpy argmax function here. Then a couple extra more imports we'll need it. Let's just import also Gradio. As you already know, Gradio is actually a great tool for interface. So we'll just try to create the interface, and this interface will let us to see how image classification can work actually in real world environment. Let's just define our function. We'll call it as image classification. So inside we'll give two images, image 1 and image 2. Then we have to first of all get image bytes. Image bytes work particularly well if you are trying to use the same model in if you are just trying to create small application in Hugging Face. So we already got like image bytes. Let's just import image from PIL. That will let us to first of all get it from the array. So image from array. We'll use image 1, and then we have to save it. Image bytes. Let's just also use some format that's going to be JPG format. Since we already got the image here, we have to also open the image. That's going to be image open. Inside we'll use image 1. We have already opened it. Let's just create a numpy image with the help of numpy array. Then we have to use actually keras utils. We'll import load image to array, then load image. Okay, let's just firstly see how this image array can work. So image final image will be actually image array, and inside we'll give numpy version of that. Then we have to get the block images. So we'll use from process import block image as well as simple CNN. So we have to use it inside here. So we'll just try to get the block image, and since we already have the block image, we can use here to get the pixels. And the final idea is actually to create the pandas data frame out of that. So we'll use a block image inside here, and then we have to also have some sort of label in order to easily classify the final result. So the label will be actually 0. So we are assuming that the label 0 means actually banana image, like so it's defining the banana image. Then we'll do the same steps for the image 2. But later on, we have to create one final data frame based on the concatenation. So we'll just use it as image bytes 1. We have to change it to image 2, image the same way. We'll put it as image 2. Let's just change the naming here. So we created the second label. This is going to be 1. And the final data frame will be based on the concatenation that we already got from here. We'll just put it df1 and df2. Then we have to have the access 0. So based on the data frame, we'll get X and Y. Our X will be actually anything other than that label. We have to drop it as per home. Then we'll use actual label itself for Y label. Then we'll need to use training test split in order to get train and test data. We'll just use it as X train, X test, then Y train, Y test. So inside we'll just put X and Y. We have to define test size. So the test size will be 0.2% as per Pareto principle. Then we have to define also random state, which will be 42. This is good for reproducibility in order to get the same randomized values. So we have to get the final model. The final model will be actually simple CNN. Inside we will have to put X train, X test, Y train, Y test. Then we have to get the final prediction. So the predictions will be actually model.predict. Inside we have to give X test. We have to make sure that predictions actually S type integer. So since we already got that, we have to get the final prediction results. So that will be actually based on the argmax function. Argmax function does let us to get the maximum results, but as per x-axis one. So here we actually forgotten the very first thing. We have to use actually two categorical. Categorical will let us to just get y. We have to also mention classes. Number of classes will be actually 2. We have to import it from utils. Since we already have that, we can just simply create the one last list that will be actually banana, and the last one will be actually berry. So let's just return out of these labels the final result. So that will be 0. And then we have to create final interface. So the interface, as you already know, will use Gradio. The function will be the name of the function that we have already mentioned here. So that's going to be image classification. Then we have to define inputs. So what type of actual inputs we'll use? We'll use image here the same way. Then we have to use examples that will be banana.jpg, and we have to have berry2jpg. Then the last one will be actually our outputs. Outputs will be text format. We have to launch this. But prior to do so, let's just first of all see how block image really looks like. So we have to take this function and let's run it in the interactive window. First of all, we have to actually have a couple of more imports. Let's just take this imports, and then let's just do a couple of extra more. We have to have the image. We can load it with the help of load image. Inside, we'll use the name of the image, which is banana JPG. Then we can simply print it. As you can see, this is the banana image. We can actually get the array format from that. So image to array function let us to get the final version, the array version. So this array actually shows a couple of numbers. Each number actually defines RGB colors that we have. So RGB colors meaning red, green, and blue. But block image does let us to get only pixels from that. Let's just use that block image as well. So inside we'll give just array, simply array. And here, if we print it out, you can see that this is only the list of the results. So each result, if you put these results to the actually data frame format, we'll have 192 columns per each array. And then we also have the one final result, which is actually the label. So based on the label, we are trying to simply do some classification. All right, let's just run our final result, which is the interface. Let's take all the code and run it. So let's run the last interface. So this interface basically led us to just create a small interface based on which we can simply drop our final results. Here's where it really gets exciting, the Gradio interface. So this library, this code sets up a simple yet powerful interface for image classification. The interface takes two images as an input and outputs a predicate label. Let's just run it first of all. All right, so you see here, we already got two image part. We can just drop simply here images. We'll use banana image. And this is the last image, as you can see. Let's just run the simple way. And you'll see here that it's actually processing. So let's just talk about this part. So the provided images are actually berry image and banana GPJ showcasing how the model performs on the specific case. So as you can see here, we are just trying to block image. Let's just first of all talk about the block image function. This extracts the features. The CNN simple actually builds and trains the CNN model, and the my classifier that we just created, the image classification, ties everything together by processing images and making predictions. Finally, the Gradio interface wraps it all up, allowing users to interact with the model seamlessly. So let's just wait for the final. As you can see, it might take a little bit time. It really depends on the image that you have. It might take some time simply because the image is really image data is really big. Specifically when you just try to get the block images, that reduces the size that you might have. So this is the final epoch, as you can see, and this is the final validation accuracy we got. This is 97%, and if you look at the output, you can see that this is just banana. So in this brief overview, we have explored the key functions, the overall flow, and the significance of the Gradio interface in this image classification project. If you are ready, let's dive into the code and see it in action. Feel free to experiment with your own images and see how the powerful combination of image processing and neural networks can classify different frauds. Happy coding.